Okay, thank you. Well, good morning. So I've been helped in this work by Demetrius, who's here, and he's been helped by lots of people. I've been helped by other people as well. So there's this cunning array of dots after his name, which is meant to include everybody who happens to have contributed to the work. Okay, so polymer physical properties is, it could be it's a very broad topic. It could include almost anything. I'm really concentrating on mechanical properties and how they're affected by the what happens to the polymer physically, how we can manipulate the mechanical properties by doing physical processes to the polymers in solid phase. And the other thing I'll be looking at is how do we analyze the behavior of such materials after they've been processed in that way, because they're not only do you improve their properties, you also make their properties more complicated as well. So we'll be doing some mechanics at a sort of elementary level, So first of all, let's I assume you don't know that much about this level of polymer behavior. So what I'm going to do, I'm going to talk about molecular orientation, its effects on mechanical properties. And let's look at the small strain elastic behavior of the materials, the oriented materials, and how we analyze it, because they become anisotropic. That makes it complicated. And as an example of the implications of that, I'll be looking at nano indentation and how we analyze that for oriented polymers. Okay, so very basically, this is how we orient a polymer. You stretch the molecules. So this is molecules are there in their random states, maximizing entropy, being occupying on average their most favorable end-to-end positions, end-to-end distances statistically. And we can obviously mechanically stretch a polymer, and then we orient the chains. So they take them out of their random positions. That takes you're decreasing the entropy, so you have to apply a force to make it work. So basically, if this is done in the solid phase, then if you then cool it having stretched it, you'll freeze that orientation in place. So you'll end up with different mechanical properties. At least they'll be different in the direction which you've stretched, and not necessarily in the other directions. They may change a little bit. So that's the very basics of it. So just to show you that how this can work, this has been going on. This kind of process has been going on for a long time. So early example from 1976. And the thing we're plotting here is Young's modulus, the stiffness of the material. So and this is for fibers. And the draw ratio, the extension you've applied, the permitted extension you've applied, it goes up to about 30. And you can see the modulus goes up. You can't see the undrawn stuff isn't actually on the graph, but it's around 1 gigapascal. And you take the modulus up to about 60. And you've only drawn it by a ratio of 30. You can draw fibers up to about 100. So you can actually take the modulus up to maybe 100 gigapascals, which is compared with steel, which is 200. That's quite significant. Okay, so and also you don't just affect the stiffness, you also affect other things, various physical properties such as thermal conductivity and so on. And mechanically, you affect the fracture behavior, because a simple, a naive thought about how this is happening. If you've got chains oriented across this way, then to drive a crack this way, you don't have to fracture so many chains as you do if you try and drive a crack this way. And you find the fracture toughness does go up, and the behavior of the fracture in an oriented body, if it's a test like this, we've got the draw direction vertical, then the cracks don't go this way normally, they'll go this way, some angle. So it's somewhere between the easiest direction, which is along the axis, and between the direction of the biggest stress, which is going to pull it apart. So it's some oblique angle. So you change and this, of course, this one, it just cracks straight across like an undrawn material. And we don't actually improve. You may improve some fracture toughness slightly in that direction, but not much. So the isotropic value for K1C is 1.5, and you almost increase that by a factor of 10 by this drawing. And of course, we've got it's around 10, the draw ratio here. And this was done by die drawing, strip die drawing. The material is actually polyethylene. So how do we do it? How do we create the oriented body? Well, so there are physically there are two sorts of oriented materials. There are amorphous materials and crystalline materials. So with amorphous materials, it's fairly simple in terms of understanding what you have to do to the material. The thing is controlled by the glass transition temperature. Okay, so that's below the glass transition temperature. The polymer chains are close together, interacting with each other, so you can't easily deform a polymer chain. You can't straighten it out because the other chains are getting in the way. So a polymer chain acts as if it's in a confining tube, okay, because of the fields produced by the other molecules. So it's got a certain radius of gyration. Well, if you take it above TG, then the polymer chains start to behave quasi-independently of each other. So polymer chains can be stretched. And if you then stretch them and cool it below TG, that stretch will be frozen into place. So you've got an oriented body. With semi-crystalline polymers, the glass transition temperature isn't so relevant. So glass transition, you can draw polyethylene, for instance. The glass transition there is about 0 degrees, and you have to take it up to maybe 90 degrees to stretch it. And you can't stretch it at 0 degrees significantly, usually, for most polyethylenes. And that's because it's the crystal structure is what holds the orientation in place. So you have these traditional picture of your folded lamellae. So you get crystal blocks, and which, if the crystal is imperfect, you can have some of the molecules going off and joining the crystal blocks together, so you end up with this kind of behavior. So when you draw a crystalline polymer, you may start off with this spherolytic structure, which is because the crystal lamellae nucleate from a point, and they grow away from that central point, and they form sphere-like structures. So here you can just about see the difference in the shade here, as you got these are crystalline and amorphous layers, and these spherulite type things. So you got sheets of polymer growing like this, and amorphous material between the sheets. If you draw the polymer, then you'll destroy the spherolytic structure and create a different structure. It creates a more fibrilla type structure. It looks more like this, and you end up with a self-supporting, really, a kind of network of polymer structure that is known as a crystal bridge type of structure, which you can imagine these are, the dark parts are crystals, and there's some continuity as you go across the material there. So that's the basics of it. Okay, I'm going to fibre spinning is one way of producing oriented material. So, okay, you make fibres. Okay, the traditional way you extrude the fibres and you wind them up and so on. And so at this point, you've got something like an isotropic fibre without a drawing, without any molecular orientation. And this is the important part from the point of view of orientation. Actually, you've got two spinning rollers at different speeds, and you end up producing a permanent extension. And this is how you get the very high orientation. So you get factors of, if this wheel's going 50 times faster than this one, you're going to get a draw ratio of 50. And this is how you get the very high draw ratios with fibres. Okay. And it's necessary, of course, that these are fairly small diameter, so you can wind them up. And it all flows fairly freely. Okay, so you have to possibly heat it up again after the cooling step, and then take it up to its draw ratio, and then wind it up. So for large sections, we can't do that, but we can draw it through a die. So this is die drawing. So basically, it means that you pull the die. You have an isotropic billet of material. You heat it up. You pull it. You may have to machine it so it fits the die for the early stage, and then you can pull it through. And this die geometry will, at least in part, it will control the orientation. So you can produce orientations of maybe 10 or 15, possibly 20 for larger sections. And of course, you can produce pretty well any section as long as you can have circular sections or sheets, eye sections if you like. So that's obviously this process has been developed since, I think, starting in the 60s. It leads and continues here. You've probably seen it on your travels today around the lab. That's how it's done. So I'm not going to go into details of how it's done, but accept the fact that we can do it. So we can produce oriented materials, to various extents with different materials, both glassy polymers and crystalline polymers. So what we maybe got that. We end up with an oriented body which has different properties in different directions. Okay? Unlike, so this is very apart from the traditional engineering materials, which was metals and glasses, and traditional isotropic polymers. Okay, so in those materials, traditional engineering materials like metals, they usually have a melt step to produce them. So they start off as a liquid and freeze liquid. So the liquid has no structure, no preferred orientation. So you end up with an isotropic solid. No one ever decided this is a good idea to have an isotropic solid. It's just the way it happens when you have this kind of artificial material. So it differs from biological materials, which tend to be different in different directions because they're subject to an evolution process. They become efficient, they only have stiffness in the directions they need stiffness, and so on. So oriented polymers are anisotropic, and so it's more complicated because you don't have one elastic modulus. You have different elastic moduli depending on how direction you stretch it in, how you measure it. And of course, the other elastic constants which we need to define elasticity are Poisson's ratios and shear moduli. So it looks like you've got 9 constants. Okay. So that's going to cause us a bit of a problem. Okay, so in traditional isotropic elasticity, you've got a Young's modulus and you've got Poisson's ratio, and that's it, 2 independent constants. So here, we're increasing it. And how's that affect the behaviour? How's that affect the analysis? So that affects how we analyse it in quite profound ways. So some of the things we casually accept may not work anymore. So I want to explore this with the example of nanoindentation. That's nanoindentation is one way of getting elastic properties. So the typical, this is relative to what you've seen, I'm sure. You end up with usually using this kind of Berkovich indenter because it's a way of making a sharp. The geometry is like this because of, I guess it's because the way of getting a sharp point is easiest if you can make 3 planes intersect at a point. So that's why it's that particular shape as a standard angle. It looks like this, and you make an indentation. Once you've taken your indenter out, you've got something like that. So there's a lot of permanent deformation there. So a lot of plasticity, a lot of plastic deformation. And yet, we frequently use nanoindentation to find the elastic properties. So we've got plasticity there, but when we do the experiments and analyse them, we do what we can to eliminate the plasticity and just get at the elastic properties. And it's basically done like this. So you measure the load and you know the displacement of your indenter as you push it into the surface. So as you increase the load, you're increasing the plastic zone. You're putting more and more yielding into the system. So as it goes down, you yield more material. Okay, so on the loading, you've got plasticity contributing to the force here. Whereas when you stop and unload, then you withdraw the indenter, so you're not actually creating any more plasticity. So all the forces you see as resulting from this unloading are because of elastic recovery. So this unloading is really a way of isolating elasticity. So then you can measure something. So if you take this slope, okay, slope is the ratio of force to distance, basically. So it's a slope similar to a modulus in a way. You know, it's similar to modulus is stress over strain. This is force over deflection. So it's, you can usually derive a modulus from that for any elastic system. And in this case, we call the slope an S, and we have this thing called, which I'll call the indentation modulus, which depends on the slope, and it also depends on this A, which is the projected area. And that's the projected area. It's basically, if this was a conical indenter, this area here would be a circle. The red line is the Berkovich. It's going to be a triangle. It's that's that area. Also involved, and this form is just the area that's involved, but by implication that also involves the penetration depth, which is this depth HC, which is not the same as how far you've driven the indenter H because the surface deflects. So how you need this HC experimentally, and it's done by complicated experimental things which Colin understands. He's not here. Anyway, it can be done. So we can work out this M, which is an indentation modulus. And this analysis, and the ones I'll show you, for all, the mathematics behind this is all based on a conical indent, because it's a nice anti-symmetric problem. You can solve it analytically. That's why we end up with this type of expression. So we take the easy way out. We use the easy analysis, because you don't have an analytical solution for the Berkovich indent. So we use a Berkovich indenter because it's easier to make a sharp point. So we've got two easy things, and they don't actually match. It's always assume that the precise shape indenter doesn't really matter. Something we can explore. Okay, so for isotropic material, we can identify the indentation modulus as m equals E over 1 minus u squared. So it's just involved with the two elastic constants, Young's modulus and Poisson's ratio. And, that's known as the reduced modulus. So it's equivalent to the modulus you observe if you're stretching something intentionally, you restrain its lateral contraction, so you stop one of the Poisson's ratio type contractions. You end up with a ratio of stress to strain, which is basically E over 1 minus u squared. So you can, if you know Poisson's ratio, you can find out what the modulus is. If you don't really know Poisson's ratio, you can guess it. It's for an isotropic material, it's going to be between 0 and 0.5. It's usually 0.4 or 0.3. So if it's in the range of 0.3 to 0.4, then this factor 1 minus u squared is going to be 0.9, 0.8. So you get a reasonable estimate just by guessing the Poisson's ratio. Right. So that's okay for isotropic materials. Now, we can do the same measurement for any material. You can get the slope, you can calculate something, we can calculate the indentation modulus. The question is, how do we interpret that in terms of this bunch of elastic constants? I mean, even the other problem with anisotropic materials is, in isotropic materials, Poisson's ratio is between 0.5. With anisotropic materials, you can't even assume that. You can get Poisson's ratio getting up maybe past 1. So at even in the extreme case of all ZT materials, you can get negative Poisson's ratio. So all the simple rules of isotropic materials don't apply. So you've got a series of problems. Nevertheless, we can deal with this to some extent by looking at materials with symmetry, so that often you'll have a material which two of the moduli are the same. So if you're drawing a material, typically you'll get a modulus along the draw ratio, which will increase in the other two, not change much, maybe equal. So in that case, you can reduce these to 2, and then that has effects on the number of Poisson's ratios you need. So continuing this, let's show some results from nanoindentation based on an oriented polypropylene. So this is drawn by us, a small scale drawing in the lab. So we produce this material, and we've drawn this. This one has got a draw ratio of 6.5. This is an example because we have done nanoindentation experiments on it. We've done nanoindentation in 2 senses. We've done it, so you're indenting along the draw direction. So you're taking relatively thick sample, so you can actually push the indenter into it along the axis, and also transversely. And we get different answers by doing that testing in different directions. So now if we assume, we're slightly crossing our fingers, we assume that the 1 and 2 directions are the same properties. So we've got symmetry here. We've got 1-2 plane is basically 1-2 plane is isotropic. So we've got that kind of symmetry. This will certainly be true if you've drawn a rod, okay, but you may get some restraint when you're drawing along this direction. So the effects will be small. So we can analyse this reasonably accurately by assuming we've got this uniaxial type of deformation. So in that case, E1 equals E2, so we just have E1 and E3 for the two moduli, and then we have, in effect, two Poisson's ratios and two shear moduli. So in effect, actually, that's six numbers, but in fact, because we've got this isotropic plane, then G12 is related to the Poisson's ratio, U12, and the Young's moduli. So in effect, we reduce the constants down to 5. So that's a kind of progress. So having done that, sorry about this. Don't worry about this, but it's when we're dealing with anisotropic materials, we tend to forget about the Poisson's ratios and use a more systematic form of Hooke's law. So these are the stresses, sigmas are the stresses, epsilons are the strains, and we've got the stiffness constant C11. So C11 is, roughly speaking, the modulus 11, E1, same with the other diagonal terms, 2, 2, and 3, 3. And these off-diagonal terms, C12, relate to Poisson's ratio type effects. And then we've got the remaining shear moduli, which we call C44, 5, 5, 6, 6. So this is, basically, it's a good idea to dump Poisson's ratios because they're confusing when, because nu12, for instance, doesn't equal nu21. And you always forget which is which. So C12 does equal C21. So we've got the symmetric type matrix behavior there. So, okay, suppose we've got these elastic constants. We can, now we specialize this down to, so that 1 and 2 directions are the same. So C11 equals C22 now. So, and so on. So that will mean that C13 and C23 are the same. And also we get the C66 will be simply related to the other 1, 1, 1, 2 constants. Right. So someone has actually done an analysis of this for this type of symmetry. So we find in the literature someone's done an analysis based exactly as before on this kind of conical indenter, and they produced an expression involving the stiffness constants for M3. So M3 means, I'm taking a 3 as a draw direction, so M3 is modulus when indenting along the draw direction. So the other two possibilities are, there's only one other possibilities for these formulas is M1, which is for indenting along transverse direction. So we've got these two formulae. Now we're not, it doesn't help us find the modulus so well as the isotropic case, because we can't just, like we did with the Poisson's ratio, so well it's going to be 0.3 to 0.4, therefore we can roughly estimate the modulus. It's not working like that, so it may not be that helpful. But let's pursue it and see if this analysis works for our. And then once you understand it, you can decide whether it's useful or not. But let's verify this and see if it helps us analyze this behavior. Because we can measure the elastic constants to some extent. We can measure the moduli. Poisson's ratio are a bit difficult, and shear modulus are a bit difficult, but as we can see, we can at least estimate those values of Poisson's ratio for this kind of oriented polymer material. Right, so we can measure the tensile properties. Poisson's ratio are more difficult. We're looking at this particular dihedral polypropylene draw ratio of 6.5. We can measure E3, which will give us one of the elastic constants. So that's about 10 gigapascals, so that's increased it roughly by a factor, from about, I guess it was around 2, the isotropic case. And so for the other measurements, we based it on an ultrasonic method, which we didn't do ourselves, but our friends at Leeds University, Peter Hine, he has a method of firing a beam of ultrasonic sounds into a solid while we're rotating it, and then you end up with a set of elastic constants, which you don't quite believe because it's much higher strain rate than we measure in static tests, but we can scale them down to meet our sort of static speed, because at least we can measure directly the modulus. So from that we get Poisson's ratios. These three Poisson's ratios, 0.24, 0.32, 0.08. So you can see that Poisson's ratios are seriously affected by the orientation. There's also nu2, 1, nu3, 1, and nu3, 1 and nu1, 3. So those are what we need to define the C's. So we can basically, and we can also get the shear moduli from this method as well. So we've got something we can use. So we can calculate that. We're still going to calculate M in the same way. The experimental method is the same. And this is what we do. What I've done at first in this analysis is look at a conical indenter. So we're simulating it with a conical indenter to check things out, to check that our finite element method is working. Our mesh is dense enough. Our procedures for getting the gradient is okay. The differentiation has done numerically, so it's checking out various things to see if we can make sure it's all consistent. And the other thing I'm not doing, I'm not including any plasticity in this analysis because it's just a nuisance. We can include plasticity in the analysis and get realistic looking indentation and unloading curves, but then you've got to just measure the unloading, calculate the unloading curve and ignore the loading curve, so it's much better just don't put any plasticity there in the first place. Just straightforward. So the unloading curve and loading curves are equal alongside each other. Okay, so we do that. We can the analysis will tell us a number of things. It will tell us the force. It will simulate the force, which is something we did. We can help us calculate the slope. We know how far we've moved this indenter. We need the projected area to use this formula. And how do we do that? But the particular package we use, Abacus, it will output the contact area here. The area of the surface of contact. The contact problem is quite difficult. In the process of doing this, it calculates the contact area. So from that, if we know the geometry of the indenter, we know the contact angle, not contact angle, the indenter angle, then we can use geometry to calculate the HC and calculate the projected area. So the essential things are there for output, and we can use this formula on the results from the FE. We get M for whichever direction we're pushing. So we get either M1 or M3. If we do that and compare it with the results for this oriented polyethylene, so for M3, this is the analytical solution from that equation, and this is the M3 calculated at each increment as we push this indenter in. So, what's happening is that this analysis improves in the sense that we get better values of contact area the more we push the indenter in. You can imagine at the start of this process, we've got the sharp indenter, 1.1 node at the end pushing against another node on the surface. So that's not really much of a contact problem. It's one node pushing against another. We don't really have any geometrical effects from the indenter, so it's not really a contact problem. And as you proceed, of course, this analysis is calculating the area based on a small number of elements to start with, so it won't be very accurate. It's partial, at the very start of this, you have partial contact with maybe 4 elements, and that's not going to do a very accurate calculation. But as it proceeds, it gets better, it reaches a steady state, so it's not changing much once you go to this once you're going to go to this depth. So this is actually millimeters, so it's my analyses are pretty unrealistic in terms of how far you penetrate it. And it doesn't matter if it's an elastic system. Just need putting in far enough so that I'll get reasonable contact. Of course, the stresses are huge because it's elastic. There's no plasticity on. Again, that doesn't matter. So M3, we seem to have nailed it. So that was the simpler of the two analyses. In fact, M3 is you're indenting down the draw direction, so it's an axisymmetric problem. So the formula for M3 is actually an exact answer, an exact solution. The analytical expression for M1 is an approximation. So we're actually comparing one approximation with another here, because in the guys who developed these formulae found it's an easy solution for the axisymmetric case, but then the other case, they had to make an assumption about the contours of stress or strain, but they are circular in the plane. In actually the axisymmetric case, they've assumed they're ellipses and fitted them. So nevertheless, it looks like we're doing the right things here. Okay, so in the right direction. Okay, so first question we can answer is this. It's been answered before. What's the effect of having a Berkovich indenter? This is a standard one, everybody uses it. Everybody's also using the expressions for a cone to derive the indentation modulus. People have looked at this and decided that by modelling that it doesn't make a lot of difference, but all those calculations, as far as I know, have been done with isotropic material. Maybe with an anisotropic material, we're going to have a different problem. So we do the same analysis, but this time we've got a Berkovich indenter with a standard angle and so on, and you see you push it in, we've got a reasonable number of elements in the contact area, which you can see there, so it gets to be, the analysis behaves in the same way as the cones, but you get higher answers. You get, at least for this M3 case, you get a significantly higher answer compared with the formula and so on. And M1 is kind of reasonable. So from now on, I'm going to use the FE values for analysing the material, assuming they're right. Okay, so let's compare. So let's compare the indentation experiments. So these are the indentation moduli as measured for M3, and as calculated from the analysis, it's kind of seriously wrong. So that's not really working. M1, that's not bad. The FE is giving a good representation. Okay, so that, there looks like quite a lot of scatter here on the experimentation, but there's also a lot of points, so the error bars are quite small. So what is the problem? What's going on? So the other thing, the other problem which is not so often talked about with oriented polymers and their elastic constants is that if you're stretching or compressing along the draw direction, you'll get a bigger modulus if you're stretching than if you're compressing. It's the way measurements show that, and you can imagine that if you've got some oriented molecules and you're tempted to make them more oriented, you're going to have to apply more force than if you're just trying to kind of buckle the whole system. So measurements show that tension independent, again this is going back to just to show you how long all this has been going on. In 1972, someone, our colleagues at Leeds, measured yield stress for oriented PET drawn from ratio 5. Okay, and they found it's quite considerably different. And more recently, these workers have been working with oriented bodies, and these are not die-drawn, they're not bone fibers or anything like that. This is just orientation occurring as a result of injection molding, which is kind of accidental levels of orientation, if you like. Okay. And they've measured yield stress against the loading angle. The loading angle is the angle of the axis of loading with the orientation direction. So we've got obviously different, considerably different yield stresses. Less work on modulus, but you can see the same paper. In fact, you can see that the modulus are getting a difference in tension or in compression. So that could well be the problem why we've got a good answer in the one direction for M1 and a rubbish answer for M3. Because there's obviously considerable compressive stresses and forces in indentations, probably dominated by, which is dominated by compression. But if you look at the stress fields from the FE, you can see the regions of tension and compression. So it is complicated, but compression is important. Can we find a compressive modulus? You know, you've got these thin strips of material, which are like less than a millimetre thick, half a millimetre, a third of a millimetre, compressing them end to end to measure directly the compressive modulus is going to be a bit awkward. So we haven't done that yet. But what you can do, what we have done, is to measure, do bend tests. And of course, with a bend test, you've got, you've got compressive zones and tensile zones, so it stretches. This is the top, which is bend, isn't it? But the top zone here is in compression, the bottom zone in tension, and you can generalize the theory of bending, so you've got different moduli in tension and compression. It all works. The neutral zone is no longer in the center. The analysis is elementary. And of course, anything you do here, you can check out with finite elements. Because it will be slightly wrong because it's using elementary beam theory and it's also got anisotropic material in there. But we can derive values in compression. When we do that, we find that the value in compression is very much similar to the value across in the transverse direction. Okay. So basically, from the point of view of the modulus, it changed it basically to an isotropic material. So in modelling this, I've just changed the. We've left with the problem. What about the Poisson's ratios and so on? So I've left them the same and just put in a different value of the modulus. And left it at that. So we can model this. We can do the same analyses with a different material law. So what I've done, I've written a material subroutine to go into the Abacus program, in which simply we use a different set of elastic constants depending on whether you've got the stress along the axis. The orientation axis is positive or negative. I'm using the deviated stress because that's one that's going to control it. All the theory of plasticity tells us that the hydrostatic stress doesn't actually. Imagine if you put hydrostatic compression on the whole thing, you're not going to produce compressive properties that way. There's no buckling effects from hydrostatic pressure. So I've used this. Okay, so if this is positive, we have tensile properties. If compressive, we have the compressive properties. And rerun the Abacus analyses. So once you've assumed this, of course, there's absolutely, with material more like this, there's absolutely no hope of an analytical solution, so we don't try. And we can produce similar FE results. Okay, for M3, just look at M3 now. See that it behaves in the same way. And this is the level we reach for the prediction of indentation modulus. And now we compare the experiments with this prediction, we find, well, we've got a better prediction. It's not perfect, but it's getting there, and it's reasonable. Okay, so I think we're at the heart of the problem there. It is the difference between the tensile and compressive behaviour of the oriented polymer. And no one really talks about the compressive modulus from oriented polymer probably because it's not much to shout about. You know, we don't orient polymers to improve their compressive behaviour. But we've got to know all the numbers. We've got to analyse oriented polymers properly and predict their behaviour as a component. Okay, so we might improve this by getting better compressive modulus because the bend test is probably needs a bit of support from more conventional testing. So there are ASTM and ISO methods for making compression tests which we can explore and generally conclude that anisotropy has to be accounted for. And also, even possibly more important, tension compression asymmetry is even a thing to look at. Okay, so that's just an example of duplication of the anisotropy and the mechanical behaviour of the oriented polymers. So, any questions?
So, talking about residual stresses in polymers, can when strengthened material, can it cause phase transformation, mainly in such as in polymorphs?
You can have strain-induced crystallinity in some polymers.
And then can it cause during the functionality of a product, can it cause some a defect like breaks? Can you see mainly in brittle materials, but like in polymers, ductile material?
Well, I'm sure it can cause problems. It can cause problems in processing. When you have crystallinity happening when you don't want it, when if you're trying to draw something and it starts to crystalline while drawing it, that's going to be a problem. But as for polymers when you've got an actual component, you're not going to strain it enough, we hope, to induce crystallization.
We have seen cases where we start with a polypropylene that has both alpha and beta crystal phase.
All right.
Yeah. And when we do dye drawing, it converts to alpha phase.
So it might change volume, something?
It's difficult to measure the volume before and after. So you can do a density test and see if there's any change in volume. If you remember when we did the workshop for dye drawing, when the material is getting really white, that means that you have voids. So that means that the density has dropped. And in most other cases, when the material maintains its color, you're like 99% that the density hasn't dropped, so the volume hasn't changed. But the crystal phase has changed though. So it's not something you can see. You have to do a DEC test, for example, to see that there's a different melt peak, and that indicates that now you don't have. So you have polymorphism, which doesn't really affect anything. It doesn't affect your process. It might affect your properties at the end. But this is just in an experimental level that we found out recently. So we don't know exactly what that means.
And which material the indenters are made? And then
It's silicone or material.
Yes,
Yeah.
tip.
Diamond.
Diamond?
Yeah, that's why those planes are so refined.
Because of the plane of the
The etching process actually cleaves down crystal planes. Which gives you that very, very controlled structure.
So 63.5 is the angle for diamond?
Yeah,
on the plane.
I forget which indices, but it's the three crystal planes.
Of the plane.
It's a single crystal plane. Yeah. That's and it also means that all diamond and Berkovich tips will be the same. There's no dutiful manufacturing error or anything. It's determined by the physical property of the material, which is.
It's modelled as a rigid surface. It's a rigid body. Don't have to put in properties.
Guys, question, John?
Yes.
The similarity between the perpendicular tensile modulus and the compressive modulus, is that purely coincidental or is there a physical reason behind that?
I think there's a physical reason there.
Right.
Your depth.
Do we know what that is then?
Well, not in detail, no. I mean, it's just whatever you have. I mean, it's obviously the orientation of molecules is affecting the modulus, and it's not a crystal phase. It's causing asymmetry.
Yeah.
As you know, the early example I showed was a PET. It's amorphous, so you get this with amorphous polymers and crystal polymers. So it's something to do with the amorphous phase. I think the naive picture, you're buckling if you're buckling a set of chains, then you're going to get the same behaviour as if you're stretching a set of randomly oriented chains. It's probably symmetry between the two. No, I don't. Someone could work on that problem very easily, I think, from a theoretical point of view. Look at polymer chains.
Okay.